All right, everybody, I think we're ready to get started. Next up, we have Andrew Till from Texas A&M University. His field is multi-physics, scientific, computational nuclear engineering, and his advisor is Marv Adams. His practicum was at Los Alamos National Laboratory in 2013.
Thank you. Since I'm from Texas, I feel obligated to say howdy. Today, I'd like to talk to you about two things. The first is a new finite element method that uses as its elements non-contiguous elements. So you think of the United States, it has the continental US, it has Alaska, it has Hawaii. Those are sort of non-contiguous pieces. So too, the finite element lives on a domain where the pieces are non-contiguous. And the second piece that I'd like to talk to you about today, which I'll just briefly touch on, is how you get that mesh. How do you get those discontiguous pieces? And I use machine learning for that. All right, so first, a teaser question. How would you represent this image efficiently? How would you store this image without having to store sort of every single pixel's worth of information? One way of doing that, you might see, oh, well, this is a field of flowers, in this case, bluebonnets. There's a lot of fine-scale detail there in the flowers, but sort of all the flowers look similar, and there's not a whole lot of colors going on there. So that might give you ideas for how you might do this. So with that idea in mind, let's go to something else that might be difficult to do efficiently, which is, in this case, instead of flowers, a whole bunch of different flowers, you now have a whole bunch of these resonances. So what I'm showing here is a cross-section, literally the size that a nucleus presents to an incident neutron versus the kinetic energy of that neutron. And all these bumps are resonances, and these resonances can be quite large. They can be factors of 10 to the 3 difference in size of the nucleus. And the reason that these occur are due to preferred energy levels in the compound nucleus. But the important thing is that they're there and that they matter, and that for nuclear engineering, we have to care about these sorts of things. I'll tell you why later. But how would you represent this data efficiently? One idea might be to split this up in energy, or to partition in energy. So you take this whole thing and you say, okay, within the set of energy bounds, I'm going to just use some sort of average. But the problem there is you need a whole lot of these energy bounds to do this well. You need a lot more than I'm showing here. In fact, you need a number that's sort of proportional to the number of resonances you have. And that can be too expensive. And so instead, what you might think is, okay, well, instead of discretizing in this energy space, why not discretize in, say, something like the cross-section space, which would correspond here to horizontal lines. And with that, your number of unknowns would sort of be proportional to the variance in the cross-section and not to the number of resonances that you have to get the right answer. So just to show that schematically, here we just have a cross-section, and you split it up based upon the value of the cross-section, and you assign unknowns based upon that. So the red band, for example, would be those energies that have a large cross-section. And if you look at that, then back down onto an energy grid, you see that, in that case, the energies that have a large cross-section, well, they're not contiguous energies. They're two sets of energies that are far away from one another. And so this sort of motivates this idea of non-contiguous partitioning might be useful as a way of representing data like this with far fewer unknowns than you might need if you wanted to represent it in energy space. So the FEDS method uses these non-contiguous domains, and you can preserve these small-scale features like these resonances with fewer unknowns. So just to recap what we've done so far. So if you have this full energy domain, and you want to partition it or mesh it, one way of doing that might be contiguously. And so you put it into pieces. In this case, there are 3 pieces. And each piece is a contiguous set of energies. What I'm proposing is that you use a mesh that is non-contiguous, where each unknown lives in this sort of non-contiguous set of energies. OK, so let's go back to this flower image and motivate this with some image compression ideas, and just show an example of how this might be done and why this might be advantageous, in case I haven't convinced you already. So one way of representing this image would be to take all of the pixels that are in some contiguous region and to take the average value of all those pixels and to use that as your unknown. And as you can see, you need a lot of final elements, which would be sort of the final pixels here, to represent this picture. In fact, you'd need the size of this final element to be on the order of the size of the image feature that you're trying to represent. However, if you were to do it with something like a clustering technique, or with something like an element where each final element could be a non-contiguous set of incident pixels, what you could do is say, choose the element to correspond to all of those pixels that have a similar color. And if you have a similar color, then very quickly, say with just 8 colors, you can get the idea of, oh, well, this is a flower field. So 2 colors, you get some idea, and with 2 by 2 pixels, absolute garbage. Even going to more pixels, you're still not getting an idea of what's going on here, but with 8 colors, you're doing a pretty good job. Now you might say, well, that's disingenuous. With the clustering case, you still have to represent where all those pixels go. And in fact, I would say not necessarily. It depends on your application. And for what we're doing, you don't really care about what your energy or what your pixel domain is or any of that. You just care about the final colors. And in that case, you can get a lot better information using this clustering idea than using an averaging idea. OK, so hopefully that's well motivated. Because now I'm going to switch gears a little bit and talk about how this applies to nuclear reactor analysis, which is sort of the case I applied it to for my dissertation. So in nuclear reactor analysis, you are solving the Boltzmann transport equation. And it's, in our case, a 6-dimensional quantity. So as in most fluids, you solve for a density. In this case, it's the density of neutrons. And the density depends upon where you are in space. So at different locations in space, you can have different numbers of neutrons. But these neutrons don't behave like a fluid. In a fluid, you can say, well, it's basically isotropic. The neutrons are in all the same directions. And also, you could say, well, the distribution in velocity or in speed space is something like Maxwellian or Maxwell-Boltzmann, something. But with neutrons, you can't make those assumptions. And so instead, you have to actually discretize in all of those variables and solve in this large phase space. And this is the reason why you need HPC when you're solving these problems, is you have sort of this tensor set of unknowns. So if you have, say, 100 unknowns in energy, and you have, say, 100 unknowns in direction space, and 100 unknowns in energy space, then you have sort of 100 cubed unknowns that you need to solve. And so here is a spatial mesh that you might have for something like a research reactor like we have at Texas A&M. Those round things, these are the actual nuclear fuel, and then the stuff out here is moderator. So that's a spatial mesh. The directional mesh, normally you solve in discrete directions, and so you have some number of directions to do, and what we're focusing on is how you do the discretization of the energy variable. And one of the hard parts about this is that the dependence of the neutron density on these variables is not separable. So if you look at the density of the fast neutrons, it's actually a flux, which is a subtle difference in density, but just think of density. These fast neutrons are neutrons that have high kinetic energy. This is their distribution, red meaning there's more neutrons around there. And for the slow neutrons, this is their distribution. Very different. And so this is why you actually do need this tensor product. So we're solving this equation, and that's what we want to do. And so let's consider a slightly more simple example that still has all the relevant details of what we're talking about. Let's talk about an advection-reaction problem. So here I've no longer have the angular variable, but I've introduced a non-steadiness to it, so there's a time dependence. So you have this unknown flux, and it changes in time. It advects with some background velocity, and it also reacts with some coefficient sigma, and then there's a source Q. I'm ignoring boundary conditions for this talk. And the issue is that the fine structure in sigma versus energy is then sort of imprinted onto or causes fine structure in the solution. So your solution has all of this resonance fine structure in it. And the things that you care about, say the reactivity or the criticality of a reactor, that depends upon what the solution looks like. So you really do care about getting the solution right, but since the data that you're putting into your problem is very fine scale, your solution is fine scale. So more generally, you could be doing anything that has microstructure. So you all have different physics than I do. I'm sure that in a lot of your cases, there are issues where you have fine scale in some variable. And so this sort of technique can be used similarly. All right, so in the CSGF, there is, of course, this melding of application, of math, and of computer science. So let me very quickly touch on what I used for the math, what I used for the computer science, and then I'll give you, if there's time, a quick result. So for the math, we do a finite element representation, which means we take our exact solution, we put it into a basis function form, and we use weight functions that are basically membership functions. They're 1 if energy is inside of the energy element and 0 otherwise, and this is what our weight functions look like. Our basis functions look like the same as the weight functions, but they have some sort of shape to them. Because our weight and basis functions aren't the same thing, this is a Petrov-Galerkin finite element. I don't really have time to go into this, but you do use standard tricks to go from the continuous equation to get a weak form of the solution, where you've replaced the continuous dependence on energy into just an index, k, which is your element index. And the cool thing about this method is the only approximation you make is the approximation that you can have a basis function representation of your solution, and then everything else falls out without any additional approximation, including definitions for the coefficients, which are basis function weighted. All right, so there's still 2 free parameters in this method. The first is the shape of the basis functions, which you could just use as flat, or you could do some sort of analytic model or subgrid problem to get a better representation. The other thing that you need is the support of these basis functions, these weight functions, which is also the definition of the elements themselves, the energy elements. And really what you want is the following property. You want to say if I have 2 different energies and I put them into the same energy element, I want the solutions to behave similarly. So I want the solutions at those 2 different energies to behave similarly for all space and time. Of course, this requires you to know something about how the solution behaves on that fine scale, but we can do this approximately. So if you assume that you can compute very fine spectra, which is to say solutions for your flux for some much simpler problem, but that has all the fine scale energy dependence in it, for several representative, say, locations in your problems, then what you can do is hand that to a clustering algorithm, and it will tell you what the energy elements are. So very quickly, if I have, say I have 2 different types of fuel pins. One has mixed oxide, so it has uranium-238 and some plutoniums in it, and I have another one which is uranium oxide, which doesn't have any plutonium but has uranium-235 in it. And I look at what, say, an infinite medium solution is, what the flux is in both of those elements, if there were just an infinite sea of both of those. This is what I get. Now, they both have similar features because there's both uranium-238 in both of these. And so what I do then is instead of plotting these against energy, I plot these against each other. And this is sort of what the clustering algorithm sees. And it says, oh, look, for energies that are of this color, these sort of have a similar behavior in both the UO2 and the MOX, so let me put them into the same element. And it does that for however many clusters you want, and that's how you get your energy grid. Okay, so what we find at the end of the day that is if we do this and we run it on these big reactor problems, we get something that's much better than the previous method. The previous method required you to have an unknown count that was proportional sort of to the number of resonances before you started converging, whereas we converge quickly, and we get to a much lower error than you would with the same number of unknowns as the previous method. Finally, I would like to thank Krell for these past 4 years for allowing me to look into a method that I definitely wouldn't have had the resources to be able to do without the fellowship. It's been a great 4 years. Thank you, and any questions?